In question 5, we're told about this girl, Sheila, who's trying to make patterns from tiles. We're given the first 3 examples of these patterns, and we're told the sequence continues in the same way. The first piece of information that we're given really about these is that the tiles are made out of a square and 2 diagonals. And before we actually start on the questions, it's probably worth spending 2 or 3 minutes just investigating what's actually happening. And if you have time in your own exam, I would recommend this. So let's look at the square first of all. In the first pattern, it's a square, it's 5 tiles long and it's 5 tiles high, as you would expect from a square. All the sides have to be the same length, so that's 5. The second pattern is moved up to 7. And in the third pattern, it's now 9 tiles long and 9 tiles high. So you can see there's kind of a pattern already, even just with the side lengths. To go from 5 to 7, you need to add 2 tiles, and to go from 7 to 9, you need to add 2 tiles as well. And what's the overall effect of this? Well, if it's a square, it's got 4 sides. Each side has to have the same thing happen to it each time, because otherwise it wouldn't end up being a square. So in terms of adding tiles, for the square, we've got 4 sides. Each of them is adding on 2 tiles each time. So the result is that we have to add 8 extra tiles to get the new square. Next, let's look at the 2 diagonals. I'm going to call that the cross. The first one, it's got 5 in it, and it's this area here. Moving on to the second one, what's changed, what's different? Well, we can kind of see the existing cross is already there. And just to make the new cross, all we've done is we've added an extra tile on the end of each of these diagonal lines. To go from the second to the third one, we can see the same thing happened. We have the cross from the second pattern sort of already here, and then there's just another square ended to each of the other to each of the diagonals. So the effect for the cross is each of the 4 diagonals has 1 extra tile added to it, so the result is we add 4 tiles on to get the new cross shape. And since that's what the entire pattern is, we don't need to consider anything else. We've done the square, we've done the cross. That's essentially all there is in this. So what's the overall effect, the total? We add 8 for the square, we add 4 to get the new cross, so there are 12 new tiles added. Now the very first question that we're actually asked in this is to write down the number of tiles needed for each of the first 5 patterns. So you can count them up. That we're given the first 2. You can see there's 21 tiles in the first pattern, there's 33 tiles in the second pattern, and if you count them up you'll get there's 45 tiles in the third pattern. And we can kind of test out the investigation that we just did. Are we adding 12 tiles each time? Well, to go from 21 to 33, yeah, we add 12. We add 12 tiles to go from 21 tiles to 33 tiles. To go from 33 to 45, rather, again, we're adding on 12 more tiles. So our theory seems to hold up, at least for the moment. So what are we going to do to get to the fourth one? Well, we're adding 12 more tiles. So we're going to 57. And for the fifth pattern then, if we add another 12 tiles, then we're going to 69. So we're adding on 12 each time. If you want, you can kind of draw out what the next pattern is in each case. You're given space to do that on the previous page. But I think it's worth doing the investigation first rather than the sort of brute forcing that is actually drawing out these patterns. In part B, we're asked to find, in terms of n, a formula that gives the number of tiles needed to make the nth pattern. So some random pattern down the line, how many tiles are going to be in it. Well, since we're adding on the same number of tiles each time, we've determined that we're adding on 12 tiles each time. That means it's an arithmetic sequence, and there's a certain formula that goes with that. That is Tn, the number of, well, in this case, the number of tiles that will be in the nth pattern, is a plus bracket n minus 1 multiplied by d. Now A is the first term, that is the number of tiles in the first pattern in this case, so A is 21 in our case. N is the number of the pattern, so it's not something that we currently know because we're trying to make a general formula that will work for any N that we put in. We do know D though, that is the common difference. It's what are you doing to the pattern each time to get to the next one. We know we're adding on 12, and I'm actually going to specifically put in the plus in this case, because sometimes you are asked about patterns where you take a certain number away each time. They do exist, and just thinking of it as a difference, you might forget that you need to have the sign incorporated into your formula. Of course, if you don't have the plus in this case, it does still work out, but I think it's just generally good practice. So I'm going to put in the things that I know into this formula. So A is 21, N minus 1 I don't know yet, and D is 12. So we got 21 plus 12N minus 12, and that is 9 plus 12N. And again, if you have a bit of time, it's no harm to just say what happens when N is 1, what happens when N is 2, what happens when N is 5. We already know from the previous question how many tiles are needed to make the first 5 patterns, so if your formula works for those 5, it's a pretty good indication that it's going to work for all of them. In part C, we're asked to use our formula or any other method we want to find the number of tiles in the 10th pattern, so that is essentially T10. Now, of course, it is possible to just take the 5th pattern and then just add on 12 and then add on 12 and add on 12 and keep going that way. I'm going to use the formula that we just generated because otherwise, you know, what's the point in generating the formula if we're not going to use it? So it's 9 plus 12 times N. In this case, N is 10 because we're looking for the 10th pattern. So that's 9 plus 120, which is 129. And if you do decide to just add on the 12 each time, maybe try both methods and see if they work out again if you have the time. In part B, we're told that Sheila has 399 tiles in total, and we're asked what's the biggest pattern in the sequence that she can make. So, essentially what we're saying is the number of tiles in the pattern has to be 399 or less. She can't make any patterns that use more than 399 tiles. So what we can do is just add on the 12 each time and then try and get whatever pattern it is that's less than 399, or we can use our formula. We know that the number of tiles needed for the nth pattern is 9 plus 12 times n, and that number has to be less than or equal to 399. So whatever the number of tiles is, it has to be less than or equal to the number of tiles that Sheila actually has. So I'm just going to scrap the Tn equals part. We don't need that anymore. And now we just have an inequality. So subtract 9 from both sides. 12n is less than or equal to 390. Divide both sides by 12. We get n is less than or equal to 32.5. So if we made the 32.5th pattern, it would take 399 tiles. But you can't really make half patterns. We're asked essentially what's the biggest pattern in the sequence she can make, and they mean full patterns by that. So n has to be less than 32.5. The biggest n that's less than 32.5 is 32. So she can make the 32nd pattern in this sequence, and you don't need to figure out exactly how many tiles are in that. It might be of interest to you if you're just sort of practicing with this question. I wouldn't bother with it in the exam unless they ask you to do it. In part E, we're kind of moving on from the number of tiles in the nth pattern, and this time we're looking for the total number of tiles in the first n pattern. So when you have the first, say, 5 patterns made, how many tiles in total have you used to make those 5 patterns? So we have to find in terms of n a formula that gives that. When you're adding up the terms in a sequence, we have a formula for that, at least for arithmetic sequences. That is Sn, that is the sum of the number of tiles in the first n patterns, is n over 2 times 2a plus n minus 1 times d. So there's nothing new in this one compared to the last formula. We still have that a is 21 and that d is 12. Because this is a general formula, we don't know n, we're not trying to get n, so I'm going to leave that sort of in the formula. So I'm going to put everything in that I know. 2 times a is going to be 2 times 21. And we're adding on n minus 1 times d, since d is 12. I put that in instead of d. So we get n over 2. 2 times 21 is 42. N minus 1 times 12 is going to be 12n minus 12. So that is n over 2 times 30 plus 12n. If you want to, you can carry it on a little bit further. You can say that that is 15n plus 6n squared by multiplying the n over 2 in there. You don't have to do it at this stage. It's almost certainly going to happen somewhere down the line, so you might as well do it, I suppose. Lastly, in part F, we're told that Sheila starts at the beginning of the sequences and makes as many of the patterns as she can. She doesn't break the earlier ones to make the new ones. So they give you the example. If she's made the first 2 patterns, she used up 21 tiles to make the first one. She used up 33 tiles to make the second one. So in total, she's used up 54 tiles. And we're asked how many patterns can she make in total with her 399 tiles. This is eerily similar to the part D, I think it was, where we can just use a formula and compare it to 399. So what we have is the total number of tiles she's used is given by the formula that we got in part E. That's 15n plus 6n squared, and that has to be less than or equal to 399. She can't make any pattern larger than that. I don't need the Sn equals anymore. I'm going to get rid of that. So I'm just going to simplify this if I can. I'm going to get 6n squared plus 15n minus 399 is less than or equal to 0. So we've got essentially a quadratic equation, or well, quadratic inequality rather. I'm going to simplify this a little bit by dividing everything by 3. So 6 divided by 3 is going to be 2n squared. The 15n divided by 3 is going to be 5n. And 399 divided by 3 is 133. And that has to be less than 0 divided by 3, which is just going to be 0. And you can use whatever method you want, really, to try and essentially solve this quadratic equation. I'm just going to do a bit of grouping. So I'm going to say the coefficient of n squared is 2, multiplied by the constant minus 133 is minus 266. So I just find factor pairs of minus 266 to try and add to 5n. So for example, there's 1 and there's minus 266. There's 2 and there's minus 133. I'm going to jump to the end here and I'm going to have 19 and minus 14. If you multiply those together, you get minus 266. If we try and add any of these together, we get, say, minus 265. In the second case, we get minus 131. And in the last case, we get plus 5, which is the thing that we're looking for. So instead of writing 5n, I write 19n minus 14n. Replace the 5n with the two numbers that will add to 5. I still have the minus 133. I haven't changed that. And now I factorize by grouping. So between 2n squared and 19n, only n is common. So I get 2n plus 19. Between the 14n and the minus 133, a minus 7 is common. And I'm left with 2n plus 19. And that's less than or equal to 0. So I've got 2n plus 19 multiplied by n minus 7 is less than or equal to 0. So we haven't quite answered the question yet. We're asked how many patterns in total can she make with her 399 tiles. So we're asked essentially what is n. So the product of these has to be less than or equal to 0, and we're asked sort of, what's the largest n that will allow this. So the answer is essentially going to be either whatever makes this thing 0 or whatever makes this thing 0. So 2n plus 19 is 1, n minus 7 is the other. Where is the first one of these going to be 0? At minus 19 over 2. The second one's going to be 0 at 7, at n equals 7. So 2n plus 19 is going to be negative anywhere to the left of minus 19 over 2. And it'll be 0 at exactly minus 19 over 2, and it'll be positive thereafter. N minus 7 is going to be negative all the way up to n equals 7. And it'll be positive afterwards. And 2n plus 19 is going to be positive if n is greater than 7 as well. So where is this product negative? Well, if we look at this first box, if you multiply a negative number times a negative number, the result is going to be positive. So I'm plus VE for positive. If n is greater than 7, then both of the terms in the product are going to be positive. If you multiply two positive numbers, you get a positive number. So we don't care about either of those cases. We want this to be less than or equal to 0. What we care about is the product being less than or equal to 0. So it'll be 0 anywhere from minus 19 over 2 up to n is 7. It's going to be negative. So what's the largest n in that range? Well, n is 7. That's the largest one. So the answer is n equals 7. And it's exactly that. And if you try, say, 15n plus 6n squared, and you say n is 7, then that's going to be 15 times 7 plus 6 times 7 squared. So that's going to be 105. So 7 squared is 49. 6 by 49 is going to be 294. And if you add those together, you get 399. So if you make the first 7 patterns, you use exactly 399 tiles. We don't need to do that thing we did before where we round down to the nearest natural n. So we just say that n is 7. So thanks for watching, and I hope you stick around for the next episode.